Hello, can you hear me? Um, you have, okay, you have, can you use the mic? Okay, Daniel. Can anybody use the mic?
Hello, can you hear me?
Okay, thank you, thank you. All right. Hi, everybody. Okay, let's, any administrative questions? Yes. Today when I go home. Yeah, he finished. Okay, all right. Yeah, for next 2 weeks, we will study chapters 7.4, 4 and 5. I will try to spread the material. So you see 33 slides, that's not for this week, it's for both. I don't know, because it's a lot. All right, let's start. Okay, so what is a convex function? Convex set. Um, and this is only defined in Rn, where you have a notion of lines. So how many have you seen convex set before? 1, 2, 3, 4. Oh, I've seen 2, 3, 7 or okay. Did you go into it or just quickly or? Okay, good. We're gonna go into it. Very good. You just can connect them with a line. So you give me any 2 points in the set, I can connect them with a line. So this is not simply connected or path connected if you've seen that. So this guy over here is path connected because you can connect X and Y. But it's not convex, right? Because the line that connects them goes outside the set. All right, good. All right. And here, continue like yes. So any line in Rn, so intervals, hyperplanes, they are all convex. Euclidean balls. And the one we're going to see in your homework is called a simplex set. So if you took 236 no linear programming, hopefully you remember that. Did you remember this? You had the parallel, yeah, the line. So you study stuff like that, right? You had this optimization set, and you followed the simplex method, and you went from corner to corner, right? Do you remember? Did you take 236? Oh, okay. Oh, it's not a prerequisite. I forgot. Never mind. Okay, so let's prove that it's convex. Okay, so let's do that on the side. So what do we mean? Take an x and y in SR. So summation of xi is R, and the same thing is true for summation of yi. I want to prove that if you give me their linear combination, so tx plus t star y, where t star will be 1 minus t in 0, 1, that this guy is also in this simplex. Okay? All right? I don't know. Can one of you tell me the proof? Kind of lazy. So how will this work? Why is it obvious? Can you see it right away? So what do I have to prove? I have to prove that txi plus t star yi is equal to r, right? Yeah? But what is is that okay? So what's the left-hand side equal to? Sums are linear, so. What? Is it hard? Huh? No, yeah, we're trying to prove that. Yeah. So summation of xi plus t star summation of yi, and this is equal to tr plus t star r, which is r. Okay, so we close the loop. Is that okay? All right. So this is called a simplex set, and it's the one of the main stuff we can study in constraint optimization, because you can imagine, right? You have some fixed amount of capital, but you're able to move your goods, right? So xi could be amounts or prices or costs, and you fix them because you don't want to mess with your cost, total cost. Anyways, a lot of applied examples can be phrased as simplices. So once you understand this, you can do many examples. All right. The union of two convex set is still convex. Can somebody tell me why? Wait, is that true? No, it's not true. Yeah, can you tell me why it's not true? Might not be convex. Where did I get this from? I don't remember. Yeah, it might not be convex. Can you give me a stupid example? Yeah, but give me two sets A, B. What are they? An example of two sets A, B. Yeah. This is A, this is B, this is X, and this is Y. There's no line connecting them in the set. I have no idea where I read this, but I caught it as soon as I read it, which is weird. All right, is that okay? So unions are not convex. What about intersections? Why are they convex? And we're gonna use this later, so I know this is true, yes. But let's prove it. Okay, let me write it with you. So if X and Y are in AB, so if X, Y are in AB, then what? Right, so there's some X of T equaling Tx, T star Y, which is in what? Yeah? N in B, right. So X is in AB. Is that okay? So since A and B are convex, this magical point called the interpolation point will be in A, but it will also be in B for each T. Is that okay? That's at the heart. But I mean, you can talk about lines, or you can talk about this interpolation, right? So the picture is you have this guy, you have this guy. Here's your X, here's your Y, and the X of T will be in both. That's all. There's nothing else. Sets can be disjoint. Yes. Thank you, Daniel. Exactly. I should look in the chat. The scale convex set is still convex. Why is that? So, okay, let's prove it. Take X, Y, and C omega. That means you can write X as CA and Y as CB, right? Then you have that AT, which is TA plus T star B is in omega. And then you just multiply by C. So C of AT is in C omega, and it connects X and Y. Is that okay? Am I going too fast? I should slow down. So whenever you see it, I mean, C omega is very specific. Any linear map will do. So you can move around your set. So it could be, C omega plus another C prime. I don't know. Right? So you can move it and scale it. You still preserve convexity. Okay, good. I don't know if you need the negative sign or the positive. I'll think about it. All right. Questions? Good. All right. Anything you can say for convex set, you can say it for convex functions. Because here's the following fact, which I didn't write, probably should have. If omega is convex, then the indicator f of x, so and f of x equal to 1 over omega x is convex. Okay, so from now on, we're just going to talk about convex functions because it includes it as well. Like, I mean, all right, we can talk about this. I mean, convex. Okay, maybe I will confuse you. Okay, scratch this. Forget about it. This is too confusing. Forget it. Yes, sorry. All right, so a function omega is convex. I have to talk about supports. It's a little bit, a lot that I have to talk about. I'm jumping. So to talk about a convex function, you need to talk about a convex set. And otherwise, this point will not be in omega. So do not make the mistake of talking about convex functions in non-convex sets. That makes no sense. Because f will not be able to be evaluated at the interpolation point. Do you understand? Okay. So this is the definition, right? And the picture is, here's the f of x of t. And here are the two points. So f of x1 and f of x2. Okay, so it says that if you evaluate at the interpolation point, x of t, it will be below the line that connects the two functions. Okay? Is that okay? So this guy is over here. T f of x1 plus t star f of x2. Okay, so this guy over here, there's an S missing over here. So this interpolation is above the interpolation point. Okay? That's the picture you should have in mind. All right, good. And the second collecting them is above the graph. All right, good. If you see strict inequality over here, we call it strictly convex. Okay, and that will be like strict global minimum later on. So all this stuff are connected. Okay, good. And if you flip the signs, the inequalities, we call them concave. So concave function and strictly concave function. Okay, and the picture flips. Now you have this. F of xt will be above the second line, the secant that connects the two endpoints. Okay. I think this is clear, right? All right. Let's do some review from Alfonso. So first year. Oh, didn't you do? No, you didn't do that. Like, when did you see convex? Only in 237, right? In first year? Oh, no way. So we're gonna reprove this. F is convex if and only if the first derivative is increasing, which is the same as saying the second guy is non-negative. A priori, you don't know the second derivative exists. You need analysis for that, and we don't have enough analysis techniques to prove this. So from now on, you can assume that if F is convex, you can assume that F double prime exists and it's non-negative. But this is far beyond our course. Okay, let's start. I will do one direction because the other one is almost identical. Suppose F prime is increasing, I will show convexity. All right, good. Take 2 points and look at the interpolation point, x of t. By the mean value theorem, you have the following. So you apply mean value theorem twice. Once between a and x of t. So you get some C1 guy. So the picture is this is A, this is x of t, and this is B. This is f of A, and this is f of B. And I'm looking at these two, and I will have a tangent line between them. So in this picture, it has to be parallel, right? So here's one tangent line, and here's the other one. F of C1. Do you understand? Shall I make the picture bigger? I think it's okay, right? Yeah. So mean value theorem tells you that there's a line at C1 tangent to the graph that's parallel to the secant that connects these 2 points. Like this. All right, good. Do the same for the other guy, xt to b. All right. And now we know that C1 will be less or equal than C2, right? Just by being in this set. Yeah, good. So F prime is increasing, and you have this monotonicity. So let me fill in what that mess there. Yeah. So this guy is equal to this F prime. Here we use that F prime C1 is less or equal than F prime C2. And this guy, we applied mean value theorem from before, and it was 1 minus t f of xt minus f of a, no, b, like this. Okay? Yeah? Do you understand? I don't know, what's the intuition? Let me see. I don't know. I have to think. Anyway, so you do that, and once you rearrange, so let me rearrange it for you. So we have t f of xt plus t star f of xt is less than t f of a plus 1 minus t f of b. And the guy on the left is just f of xt. Okay? Let me write it here. So let me write it over here. Okay. I mean, I'm gonna do this again for multivariable, so you're not missing. But I want you to understand the main idea, because we're just gonna do it for gradients, and it would be the same idea. All right. So indeed, the interpolation point is underneath the secant, connecting f of a and f of b. All right. Questions? Zoom. All right. Yeah. Okay. All right. So why is the exponential convex? What's the second derivative of f double prime? Yeah. Okay. Thank you. Here you need the a greater than 1, because if you take it twice, you have x when you have this guy over here, and you need it to be positive. Okay. All right. What else? Log 1 over x, another famous guy. So what's the graph? So this is 1 over x, and this is log. I have to so it goes like this. Right? I just took log of x and put a minus. And if you take derivative twice, what do you get? Huh? So one, yeah. Yeah, so you do it twice and you get 1 over x squared. Yeah. Yeah. So you need the minus because you pick up a minus from the 1 over x. Good. So log of x is not convex. Log 1 over x is. That's a tricky concept. Another one I have to talk about is called entropy. If you're in probability, this shows up a lot. Entropy. I don't know how far you're going to go into statistics. So take one derivative. I have log of x plus 1, right? Yeah. And then 1 over x like this. And this guy is non-negative. Okay. So this is called the entropy function. Yeah. Thank you. Yes, of course. No infinities. Question? All right. All right, this is 1D so far. Multivariable. The norm, any norm, is convex using the triangle inequality, but you don't know what a norm is. So for now, we're just going to talk about Euclidean. But so let me prove that this guy is convex using just the definition. Because I haven't proved you yet the second order condition. So let's do it by hand. So the claim is that Tx plus T star y is less than Tx plus T star y. Okay? Have you seen triangle inequality? Okay, fine. I'm just gonna state that. So by triangle inequality, if you haven't seen it, just let me know. By triangle inequality, this is equal to Tx plus T star y. And then norms are linear. Okay, so you get this guy. Okay, so this is linearity. It's actually called homogeneity. And we didn't use anything about Euclidean. So a norm that satisfies these two properties is called a norm, and it's always convex. What's another norm? Okay, yeah, 2 to 4, that's right. So here's another, yes. Norm of x equal to x transpose ax for a positive definite. Okay. I mean, we are an applied course, so I have to do applied stuff. In statistics, this is called a covariance function, right? With a Gaussian covariance matrix. Anyway, so this is another norm. It's also a norm, but it's hard to prove. You need the 2 to 4 stuff to do it. Okay. All right. The maximum function, we will talk about it. Shall I do it now? Yeah, let me do it. So let's see. The maximum function is convex. So you have f of tx, t star y. This is the maximum of tx1 plus t star y1 and txn t star yn. All right, can someone tell me why is this less than t maximum of all these xi's and then maximum of the yi's? What's the middle step? How do I do it? Is guaranteed what? What? may not appear. What do you mean same time? Oh, okay, I think I know what you mean. So, yes. Yeah, so you have to look at them individually. I think you're saying that T of xi, T star yi, like this is like y2 for, so for each I, this is less than T maximum of xi plus T star maximum of yi, right? Is that what you said? Because this could be like y2. And they don't, oh, I see, you bump them individually. Yes. Well, okay, anyway, so, but then, right. So each of the components is bounded by this number, and this number does not depend on I. Okay, I don't know however you want to think about this. So, yeah, that's the proof. Because for each I 1 to n, we have, if you like, pointwise bound. Okay. And this guy does not depend on I, the bound. So you can take its maximum. Whatever you like. Right, in general, in the maximum, if you have maximum of fg, and you know that f is less than b, and g is less than a, you can bound this by the maximum of ab, or ba, sorry. We're doing something similar here. But ba is constant, or anyways, same trick. And the constant is the same. So let me call it a. Okay, it's like this. All right. So we do this trick where we bound f and g by the same guy, a. This is a. All right. Is that okay? I just want to break it down because people want to see like step, 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 step. There are no secrets here. Okay, good. All right, good. I know I'm going slow because I want to go slow. This is material. This is our main course material. I mean, and this course is supposed to be a bird course. So, good. All right. F of x equal to log of sum exi is convex, and I mean, if you can prove it, it would be amazing because I have a 2-slide proof. So I don't know if you have a, yeah, this is tricky. So this one, we'll leave it for the end. We need second order condition. All right, anything else? Yeah, let's go over some properties. So if you give me two convex functions, their sum is convex. In fact, if you take any conic combination, it's called conic because the coefficients are positive. So if you give me any functions and you multiply them by some weights, usually these are denoted by weights in applications, and you preserve convexity. Okay. All right. So we might prove it. I think it's pretty easy. We talked about the maximum. So this maximum is still convex. That's another property. We'll prove some of them, it's fine. So I prove it here. Let me prove it here. All right, let's do this conic combination. So we have that h of x of t, because I'm tired, is summation of ai f of xt, okay? Do you know what x of t is? Do I have to say it? So then, okay, so you have this, and by convexity of each one, this is less than ai of t f of x0 and t star f of x1, okay? And then you use linearity. Okay, good, easy. All right. The maximum is still convex. Okay, one of you should be able to do this. I mean, it's the same idea. We just talked about it. So I want to see if you understand what's happening. So why is this maximum still convex? No? Oh yeah, you know. So can you tell me a little bit the proof? What shall I, how will the proof go? We take some x of t and we have maximum fi x of t. What shall I do after? Yeah, so how, yeah, but tell me. So what will I do here? What will be the A? Like what will be the uniform bound? Like what would be the uniform bound for the FIXT? Yeah. Okay, okay, how would you prove it? Yes, tell me. Yeah, why? We're trying to prove that. Sure. So how will, yeah, but tell me the proof. Anybody? Do you know? I mean, you just talked about it. I just want you to like, oh, okay, let me, yeah. Yeah, like for all I, what did you say? We have that f of I x t is less than t f0 t star f of x1. So what shall I do next? There's one more step. Perfect. Okay, that's all. Good. Thank you. Let me call it J, so that you don't confuse it. This is a different variable. It's not I anymore. Do you understand? All right, good. Questions? Use convexity, then linearity. No, maximum is not linear. What's a good example? Maximum is not linear. Okay, here's an example. X minus X is 0. The maximum of X minus X is 0. The maximum of X minus maximum of X is infinity. for x non-negative. No. Okay, what do I want? I can break this. Give me a second. I need x goes up to infinity. First of all, the minus is not allowed. Yeah, let me do it this way. Maximum of minus x, like this, yeah. This guy is plus infinity, but then the maximum of minus x is 0. Yeah? So because this is x and this is minus x. Okay? So maximum is not linear. Is that okay? I meant constant linearity. No, but you don't just have, you also have a summation over here. So you have a summation, you see? Okay. All right. All right. If f is convex, get a serial number. Oh yeah, question, yes. Yeah, otherwise this is meaningless. Yeah, of course. Thank you. I'm just tired of it. Yes. Yeah, so consider the what is called sub-level set. So let me draw a picture. Here's the exponential. Okay, and take C to be 1 or 100. Then this is e to the x. Then the sub-level set. Oh yeah, I can ask you that. Can you tell me what it is? What is gamma 100 x in R so that e to the x is less than 100? What? Yeah. Huh? Yeah. So these are all the x's less than log 100. Do you understand? Let me go. Is that okay? So sub-level set is about the domain. Don't confuse that. It's not about the graph. Even though you in textbooks they draw these pictures that I just drew, it's always about the domain. Okay, that's a common misconception. Questions? Okay. And this set is still convex. I'm going to prove that next. And if you take all of these constants, you get what is called the epigraph. So let me write it a little bit better here, because this is confusing. So you take all the x t in omega cross r, so that f of x is less than t. Okay, so I know this will seem confusing. These are two different things. So yeah, so let me draw sub-level set and epigraph. So we talked about, this is the sub-level set, log 100. And this guy over here is the sub-level set, gamma 100. Sub-level set. versus epigraph of e to the x. The epigraph will be all the t, so you give me all the points xt, such that t is above f of x. Okay, so here's the epigraph. Oh, too thick. Okay. Does that make sense? So epigraph is in the graph, is above the graph. Sublevel set is in the domain. So they live in different spaces. So this guy lives in the domain of the function. I'm just saying because I know there's confusion about this. And epigraph lives in the range. So domain cross range. Let me say it that way. Does that make sense? Questions? Zoom? Isn't that just a graph? No, no, the graph, thank you. The graph is the line. So you look at everything above the graph. Is that okay? Charlie? So everything above the graph. Okay, good. And this guy is also convex. And finally, a very nice result, which we care about. If the set omega is convex and your function is convex in omega, it doesn't have to be omega squared, you just need both to be convex. So in case you come back later, this can be omega 1, omega 2. But they both have to be convex. Okay. If you have this and you take a supremum over one of the components, this function is still convex. Okay. If you remember a little bit from a few weeks ago, this is how our optimization problems look like. We have the optimization set, and we have some, where is it? Yeah, and we have some confound variables like inflation rate. And this guy was the minimizer. So the minimizer was arg sup, whatever, of some function y. Remember, we applied the implicit function theorem and blah, blah, blah. Anyways, this guy is still convex. That's very important for us. That when you take supremum, it doesn't mess out the convexity. Question, yes. What is what? Oh, yes. Good question. What? Yeah, but you don't know that. You threw me off. Supremum of, so supremum of a set, yeah, I should have done this. So take A in Rn, then the supremum of A, oh, in R, there's no such thing as supremum in other places. Supremum A in R is defined as the greatest, the least upper bound. Okay, i.e., a constant m in R such that A is less or equal than m. Okay? If m is in A, this is maximum of A. Okay? So if m is in A, then supremum of A is equal to maximum of A, which I think you know, right? Good. And when they say least upper bound, that means if you give me another bound, m prime, i.e., you give me some m prime bigger than a, then m will have to be less than m prime. Do you understand? So that's why it's called least upper bound. Of course, you can find the upper bound, just take any number, but it's the least one. So the picture is here's A, here's M, and here's M prime. Okay? So M doesn't have to be in the set. It just has to be right above it. So for example, the set AB, the supremum of AB will be what? Huh? B. But B is not in the set. Right? Right? Is that okay? Yes. Oh, a function is in the range of the function is in R. Yeah, so okay, fine. Let me talk about it. So then supremum of x, f of x, in some set A will be the supremum of f of A, right? So this is A, and this guy here is f of A. So then this is M, and this is M prime. Do you understand? Yeah. Yeah, this would be a number. So suppose that, yeah, let's do an example. Take A to be 0, 1, and take F to be e to the x. Can someone tell me what is f of A? No. F of A. F of A is a set. Sorry, what? Yeah, it will be the open interval 1 to E. So what's the supremum of f of A? E. Okay? Zoom? Is that okay? Yes. There's no such thing as supremum for Rn. Yeah, supremum is only defined in R because of what you said. Take like a rectangle. What the hell is a supremum? There's no such thing. You had a question? Huh? Oh yeah, sure. Sorry? You mean this guy? Yep. Oh yeah, you're right. Let's do an example of this to make it a little bit nicer. I will come up with it on the spot. All right. I need a guy who's convex in both. Take the stupidest example, e of x plus y. Okay, it's convex in R2. Yeah. Then take g of x to be, but take some bounded interval because this is too much. Supremum x and no, okay, y in 0, 1, f of xy. Yeah. So then this is EX plus Y. Can someone tell me? Yeah, you can tell. What is that equal to? You can compute the supremum here. Like we just did it. Like 2 seconds ago. Yeah, so what's the bound? No, for X, we're evaluating supremum in Y. Yeah, exactly. So the maximum happens at 1. Perfect. So that's G of X. Good. All right. Zoom. Okay. That's the picture, epigraph. All right. I took it from Wikipedia. All right, let's prove a bunch of stuff. I'm going to prove the sub-level set is convex. So again, let me, so again, is it here? Anyway, so gamma C, in case you want a reminder, is all the x in omega, so that f of x is less than C. Again, this is a subset of omega. I know this can be confusing, but this is in the omega. Epigraph is in the range cross omega. All right, we want to show that the thing is convex. So you pick any 2 points. Like, let me go back to our example. Log 100. Right? So you have x1 and x2, and I want to connect them with a line. I call it x of s. Okay? I mean, for this is obvious, but in general, yeah, we don't know. Okay? All right, good. Your guy is convex. So I'll just compute it. And so the first step is by convexity. And the second step, I'm using that x1 and x2 are in gamma C. So f of xi is less or equal than C. Okay? Yeah. I think I've done this proof about 20 times. Like, I mean, with you guys, like the same argument. Okay, anyhow. But it's good. It's a bird course. Yeah. So yeah. So you bound by C, and then these two cancel out. All right. So how do I conclude from here? What did we just prove? Just to see if you follow. What were we trying to prove? We're trying to prove that this guy is in gamma C. Did we prove that? Yeah. Why? Because why? Yeah. Is that okay? Good. So the criterion, anyways, yeah, that was the criterion. So yeah, f of x of s is less than C. So x of s is in gamma C. That was the definition of gamma C. Sub-level set C of f. All right, that's good. Now I'm going to prove the following fact, the one we just talked about, that the function gx defined as the supremum over a convex set of a doubly convex function is still convex. This is not obvious at all. So yeah. Okay. I could do it the way we talked about 10 minutes ago by bounding each of the components, but this is a supremum and you have uncountably many elements, so you can't do that anymore. Okay. Anyway, so I'm going to use another proof with the epigraph. So this is the epigraph of the function by definition. I don't like the way I write it. Let me write it a different way. So this is x c in omega cross r. So that g of x is less than c. Yeah, that's much better. I don't like the unions. It gets confusing. So, okay. What time is it? Oh my God. Okay, can we take a, okay, I'll finish this and take a break. You guys can tell me. I don't know, my brain just keeps going. I don't have your, okay, I'll finish this and we take a break. That's crazy. All right, so this is the epigraph of the function. And you come back to supremum. So this is the supremum, that was the definition. So what is it saying? It says that for each y, for all the y, this is bounded by c. So just take 2 points, okay, not to confuse yourself. So it says that f of x y1 is less than c, f of x y2 is less than c, and so on, okay? So they're all less than c. So you can take their intersection because you're asking that for all of them, right? Yeah? Okay, so how do I finish from here to conclude that the epigraph of G is convex? So forget this union. So I should write it as XC. So let me write it here. Y in omega XC in omega cross R f of xy less than C. Why is this convex? So again, let me write it more suggestive way. This is equal to the intersection of y in omega of LC. Gamma C, the sublevel sets. So why is this convex? Zoom people, class people, any people? Yeah, okay, good. Gamma C is convex. And we drew these nice pictures that intersection of convex is convex. Because intersection of convex is still convex. Yes, thank you, Daniel. Man, good. Everybody got it. All right. Okay, let's take our break. Oh, right, because you wanted, yeah, it's a little bit tricky, right? You wanted, what did you say? Wait, have we talked about global? No, we're gonna do it, right. Where's, oh, it's this week. Wait a second. Did we talk about global meme? I forgot. We did, right? Well, no, just do the, okay, I will make an announcement. Because we're gonna do global meme this week, so, but the local meme is fine.
And so if it's an interior point, you just have to show that the weight is at
Right, yeah, that is easy.
If it's a boundary point or has. that-
Well, then you
that
just need to
is
sh-
necessary.
Right, you just need to have it present with every physical direction.
So we don't have to worry about global wind. That's just-
Is there a way to do it with what we know? Can we do global mean with previous week material? No, right? Like the global mean, don't you need convexity to do it? Did anybody did the homework?
Yeah.
Did you do the global mean? What? Right, so we haven't, but no, because I'm gonna make an announcement that the global main stuff is for next. Because I don't think, are you able to do it? No, right? You need convexity. How are you gonna like talk about? Right? Other, if it does stuff like this, then. Okay. I mean, if you show that the, okay, let me say this, if you show that the ball has infinite radius, then yeah. But how would you do it with our, okay, what was your idea? I mean,
No, I think for that question, it was like.
no, but how do you know, yeah, okay, fine. Right. Were there other with multiple ones?
There's another question where it says show that there's two global minimums and then one stationary. minimum. So how would you?
No, I agree. You don't have the machinery, yeah.
Because I think someone posted on the answer and then he said something relating to convex.
Yeah, yeah.
Yeah.
Was this function convex?
Pardon?
If it has two local main, it can be, okay. You can't really have. Can you do it with? No.
I'm kind of
What's the question? What did it say?
running back to this. Show that the solution has X greater than
Sorry, what? What is the example two? I don't know. And,
So it originally was actually greater equal to 0,
Uh-huh.
and then some plus x greater equal to 1. So they just, the previous example, they just showed where you just let the gradient equal to 0.
Yeah.
But in this case, so this greater, I mean, you can for this. but
so,
it's easier.
wait. Oh, I see. You're saying that the first order doesn't apply?
Yeah, like I'm confused how we should.
What is, I'm sorry, confused. The question is, you have a system or what?
Yeah, we have this equation,
That's not, that's a function.
a function,
And you
take the gradient.
What is H? What is H? Oh, it's the H, this guy. Oh, you have to show it. Oh, that what, that the minimum is contained there or what? Is it the same question?
It's the second question.
So, okay, so what happened when you set it to 0? It didn't work or
When
what?
you set it to 0, you get this.
Is it one of the
So
equations?
this is one of the equations.
Okay.
One.
Right.
But how would you get this? Oh, I know.
This will be positive definite, right? Well, I mean, there's a bunch, right? Okay. This is inequality, right?
Yeah.
But we also have an inequality for the gradient, right?
Right. What you want and for this
Right. Okay, so you're in the boundary, that's right. That's right. Oh, wow. So what's the boundary here? No, you drew a boundary, right? No, like, I mean, the physical direction, like, how did you,
So that's not it. So like that's one and
so where's the boundary here?
the boundary is
What is that, like, y equal what?
x1 meter.
Oh, this is the, oh, I see. And you said y to be this, the summation? of the two?
Yeah.
Oh, I see. Well, I mean, really,
a question because it's not very close.
yeah, this is a convex guy. What?
Yeah.
Like this guy is convex,
Yeah,
right?
it's convex.
Yeah, yeah.
You don't need to like how.
You don't even need to use convex, you just,
Yeah,
you
it's
just
like
come
high
up-
school math.
yeah, exactly.
But just one looking at it.
Yeah, you just look at the guy. I mean, no, this one has a unique global, no, but you said there's another one with two
Yeah,
local.
I think the one she showed, that's the complete square. Yeah, two squares. We get two local.
For that guy,
Uh,
which looks like high school,
yeah, it's like high school math.
no, but I thought that only has one local minimum, one global, well, what's the other one?
Two local minimum because.
At the boundary or?
It's x squared minus four and yeah, it's plus what? We got minus two and.
Nice, of course, yeah. Oh, that's right, plus me. Ah. All right. Okay, so let's start. Yeah, you guys can talk after. Let me. So we're gonna prove a condition for convexity that you will never use, because hopefully you will understand the Hessian one. This is just think of it as a lemma or for proofs, but please don't try to. I mean, I don't see a way to use it. So F is convex if and only if you have the following inequality. Okay, how the way you should think about this is that we did mean value theorem, and the Hessian was positive, so that's why we get right. So remember the second order mean value theorem. I mean, I'm not going to use it here. I'm going to have another proof, but just remember what it was, right? We had y minus x Hessian at some point C, right? This was mean value theorem, yeah? Yeah? And this guy over here, we're going to prove 3 slides later that it's non-negative. Okay, so the C1 condition will follow from the second order. But I just wanted to write it here. Okay, can I go on? All right, let me prove it. So this is nice for proofs and intuition. It says that if you give me a point, I should draw it here. Give me a point a little bit ahead, like f of x. So this is x naught, and this is x. Then the graph of the function is above the tangent line. Okay, I mean, we talked about this, right? About the x of t being below the secant, but this generalizes to higher dimensions. So I should have put it here. So here's the one you just gave me. It could be like x minus 4 squared plus y squared without the x squared, because I don't know how it looks. This guy is convex, and you can do it with an eye test, because the tangent plane at any point is below the graph. And below means outside the graph. So you're not in it. If you move a little bit north, you hit the graph. What? So if you, okay, let me specify below, because people will kill me. Below means normal to the tangent plane. Okay, so below means following the normal vector to P, tangent plane. Let me draw a picture. What's the stupid picture? Let me do it. Suppose you look at it from the side. This is your tangent plane, and this is your normal vector, n. And this is the same slice. So if you move a little bit, the normal vector, you will hit the graph. Okay, so this is what we mean by convexity in higher dimensions. Tangent plane eventually hits the parabola. Just think of your whoever took 236. This is the line method. Remember, you had the first time that it hits the simplex. You had these parallel lines. Do you remember? The sweeping plane. Okay, whatever. Man, you guys like just come in and go. Like, do you remember anything? I don't remember either. So what am I talking? I just remember sweeping plane. Okay. No, it's hard to remember. You have to apply it. All right. Let's prove what I just talked about. that convexity is the same as this inequality. All right. By definition of convexity, you have this inequality over here for any 2 points x, y, right? So you're always below the graph. So this is f of x, f of y. And we rewrite this like this. So I moved, what did I do? I moved f of x to the right, left. Yeah. Okay. And I factor out the s. Okay, you'll see why in a second, because I want to get the ratio for derivatives. Yeah, I should say it here. So the guy on the left is the following: x plus s times some guy a minus f of x divided by s. Okay, is less or equal than f of y minus f of x. Yeah. Now take limits. What is that equal to? What is this ratio limit equal to? By definition. Huh? What? What? Yeah, thank you. I thought people will forget that. Dot it with a, which is just y minus x. Yeah. Okay. Yeah. Zoom. So you have this, and that's all. That's what we wanted to prove. Okay. The intuition. Do it everything for 1D. So it's the same idea. You can also prove it with mean value theorem. Okay. And like this S could be the mean value between Y and X. Good. Now let's go from that condition to convexity. Now that's more interesting, requires more work. So take 2 points, x0, x1. This was our assumption, and we want to show convexity. So I want to show that f of x is less than f of x0 plus s star f of x1. Okay, that's what I want to show. And I wonder if I can ask you. Anyhow, so we apply it twice. Okay, from here, I think I can ask you. So can someone tell me how to go from here to this? Yeah, with some stuff. How do I first get this on the left? Yeah. Good. And then yeah. But then when you add them, the s plus 1 minus s becomes 1. Okay, and then the stuff over here would be gradient of f times s x naught minus x s plus 1 minus s x1 minus 1 minus s x. Okay, can someone tell me what this whole thing equals to? It's very easy. It's a number. Zoom, what is that equal to? The simplest answer you can think of. What is it? Huh? Zoom? It's 0. And that's because f of x naught plus s star x1 is x, and xs plus 1 minus sx is x. So they cancel out. Okay? Is that okay? All right. Good. You can do it. Yeah, we multiply, we add them. Anyways, I did the whole proof. Yeah. So then here you can say these two cancel out. All right. Good. All right. So this is the C1 characterization. The tangent plane is always below the graph of your function. So tangent plane. All right. That's the one you're going to see wherever you go. The C2 characterization, because it's the easiest to check. So your function is convex if and only if the Hessian is positive semi-definite. Semi-definite because you allow it to be 0. The 0 function is convex. So any constant function is convex. So any linear function is convex. So we allow 0, right? So just to be clear why we allow 0, so you don't have to ask later. We allow 0 because f of x equal to ax plus b is convex. And the second derivative is 0. Okay? Like, I mean, pictorially, it's convex. It's a line. So every line is itself. I mean, it's a hyperplane, but anyhow. Okay. Questions? All right. I should remind you positive semi-definite. So we had the following conditions. A is positive semi-definite. We have the following conditions. What is it? One was the eigenvalues are non-negative. And the other one was the determinants of leading minors are non-negative. And leading minor is you keep adding from the top right, top left. So you go like this. This is 1. That's another one. And it keeps growing, okay? Remember? All right. Please review it. We talked about it. Okay, good. All right, so that's positive semi-definite. But usually we'll just do it by hand. So namely, we will simply compute V transpose Hessian V, and we will show that this guy is non-negative. Okay, so in our course, we will mostly see this condition, but you're free to use the other ones. If we do 2 by 2, use the leading minor because you just have to compute 2 determinants. Question? Oh, yes. The Sylvester criterion, that's right. Thank you. Yes, I'm sorry. I remember now. This was only for, thank you. Let me say it, only for, thank you. Yeah. I don't remember the counterexample, but yes. Okay. All right, questions? I want to stretch this material. I don't want to go fast. Okay, so I'm going to show that if your guy is convex, then your Hessian is positive semi-definite. Suppose not. Suppose that you can find some x so that this matrix A would be negative. So when I say negative, I mean V transpose A, V would be negative. Okay, because it's exhausting to keep writing V transpose A V for all V in Rn. From now on, we're just gonna write this, and you're free to write it as well. And we just mean this statement over here. Okay? Do you understand? Good. All right. With a loss of generality, take it in the interior. Okay, can someone, I can explain it, but can someone tell me, suppose this is your domain and X is at the boundary. Can you give me another point Y so that the Hessian of f of Y is strictly negative? I know I write these things, but I want to see if people understand. How would you do this? Suppose that grade Hessian of this guy is negative. Find some Y so that this is true. How will this work? Yeah. Okay, let me state it in another way. Let's go back to one dimension, okay? Because we're going to do this argument, so I want to make sure people understand. Here's my question. Suppose that g of x is negative, and let me call it a, all right? And this is the interval ab. Well, even easier, 0, 1. Can you find me? So this is the function, right? It goes below. Okay. Can you find me a y strictly bigger than 0 so that g of y is less than 0? How would you prove it? Right. So let me spell it out. So G0 is less than some number, let's say, I don't know, minus epsilon, okay? For some small epsilon, yeah? This is the last time I will do epsilon delta, I promise. My hand on the, you'll never see this argument again. Then by continuity, there exists delta positive, so that if x minus y is less than delta, g of x minus g of y is less than what shall I take? Over 2. So then we have the g of y is less than g of x plus epsilon over 2, which is less than minus epsilon plus epsilon over 2, which is minus epsilon over 2, which is negative. Okay? Good memories? Yeah? I love this stuff. It's cool. Oh, if the gradient is equal to c for some c negative, take by continuity the gradient of... Right, yeah. Me and Daniel, you should get a mic. You have such good comments, and I forget to look. I will find a way to make that the chat makes a noise. I will do it next time, I promise. I'm sorry, Daniel, this will never happen again. I'm very angry. I missed your beautiful comment. I will make it so that it goes like beep. Okay, good. Anyway, so if it's in the boundary, you can move a little bit in, all right, with this continuity argument, because you can draw a ball around it of size delta, and you have epsilon over 2 error. All right. Anyhow, so that's this technicality. So take y to be close enough to x by continuity. And right, so what do I want to say here? Yeah, I mean, this is a lot of stuff that we, so let me prove it to you because this is hard. So we know that V transpose Hessian of f of x, V is negative for all V. Okay, that's what this tells us, right? And now here, take V to be y minus x, all right? That says that y minus x, Hessian of f of x, and y minus x is negative. So step 1, step 2. But then by continuity, take y very close to x, so that Hessian of f of x is very close to the whole thing they wrote over here. Okay? Do you understand? I can go into epsilon deltas if you want me to. I can, and I will give you the epsilon and the delta that will work to make them close, but I think that would be overkill. I mean, only some people took 1 through 7, so I'm not gonna bring back good memories. Okay, so, but anyhow, so we pushed from, this is a contradiction argument, and we made it from pointwise to a to a local problem. So now we have it for an entire sequence. So you will see this argument many times because contradiction says if you want something to be true for all points, the contradiction is that it has to fail for 1 point, but that's not enough for the proofs. So we use these continuity arguments to get a whole ball of them. Okay, do you understand? Because you're going to see this so many times. It's the same argument. Contradiction, there exists an X. Okay, now give me a whole chain of them. So here's a whole ball. Here's X, and take all these guys inside. They all satisfy negative definiteness. All right. This is a hard proof. This might be the hardest proof you'll see. All right. Again, let me remind you, we're trying to prove the most important result, that convex implies that the Hessian is semi-definite, just to have it in mind. And we did this by contradiction. We said that there exists an X naught, so that Hessian of Fx naught is negative. Okay? All right, good. All right, so we have this statement. Now apply second order. So just to remind you, second order said that there is some mean value of this form. This is the mean value, right? But let's combine the two. So combining the two, you have the following upper bound: f of x gradient dotted with y minus x plus 0. Is that okay? Yeah. And then what am I doing? No idea. Good for you. Oh, right. Yes. Sorry. So we got this in the, but then this is what we just talked about, right? So remember we had this C1 condition that said that F is convex, even only if the tangent plane is below it. So F of Y is bigger than F of X plus the gradient dotted, right? So we broke it. We broke the C1 characterization. Does that make sense? This is a proof by contradiction. And I needed to use continuity because, like in your quiz, theta is abstract. So you can't really work with it unless you prove it for all of them. So here we have to get a whole neighborhood. Okay, I don't know. Questions? But anyways, I think this is pretty cool. Now let's do the converse. Now I'm going to show you that if your guy is positive semi-definite, then your function is convex. Okay? Yeah, this is the main result of all this old stuff, because you will have to check this to get convexity. All right, let's go. Mean value theorem. Maybe I can ask you how to do it. Yeah, let me ask you. So how can I use the C1 condition to get that the guy on the right is non-negative? That this whole quantity is non-negative. What shall I do? No, we're given that. Oh, yeah, we are given that. Okay. I'm so lost. Right, so then this is bigger or equal than f of x times this. Right. Okay, so how do we finish from here? Yeah, this is the C1. Yes. So the C1 condition is mostly for proofs, and the C2 is for applications. So if you go to the textbook, both of them, the Perchakis and Lu, they always check Hessian, positive semi-definite, because it's much easier to prove that than to prove an inequality for the gradient. That's much harder. Yeah, good. All right. Now, last few minutes, we'll do some examples. Anyways, let's start with this. Can somebody tell me, the answer is very easy, so don't overthink it. Can somebody tell me what's the Hessian of F? Do not overthink it. The first thing that comes to mind. What? What? Huh? So what is it? I mean, we take derivative, so what's the Hessian? Yeah, it's just A. Is that okay? Yeah, it's a constant. Do you want me to compute it? Let me just do the gradient just to see if you understand. So this is all partial derivatives, right? Can somebody tell me what this x transpose AX is equal to? Suppose A is AIJ and X is XI. Huh? Okay, I'll do it. It's a double sum IJ and it's XI, AIJ, XJ. So then when you take derivative in, let's say, partial K of F, you're only left with, okay, let me do it. I always get thrown off. Yeah, right. So KJ XJ, J1 to N. All right. So if you compute the gradient, you get AX plus Q. Okay. And if you do it again, you're left with only this. All right. I want to go slow, so I'll stop here. Transpose. Oh, no. Oh, that would be pretty cool. Wow, that's hard. Yes. Okay, good. Thank you. I will upload.
Hi, Professor. Hello, Professor.
Go ahead.
I have a question about the derivative of the x transpose AX.
The derivative. Yes.
Because I think the derivative should be AX plus A transpose X. I don't know why the derivative is AX.
Yeah, it would be a vector, right?
Yes.
Sorry, what's the question? Like, why is it, like, why, you're asking why this is the answer?
Yeah, I'm asking the first part, the AX part.
Yeah, let's do that. So, X transpose A, X, is equal to this guy, right?
Mm-hmm.
Now let's take derivative in xk of this whole thing. What do I get? So let's do it step by step. Oh man, I keep having to think about this. So if I is not k, and then you have j, and then I need plus xk a kj x x j. Is that okay so far? The way I split it?
Yes.
Okay, so now take derivative of the top guy. You're only left with I is not k, xi, ai, k. And the other guy is akj, xj, right? Right?
Yeah.
So then, wait. So k, wait, I have to split it further. So you see, this is hard stuff. So this is j1 to n plus xk, akk, like this. Is that okay now?
Yeah.
All right. Now let's bring it together. So I split it like this, and the guy on top becomes I1 to n of xi aik plus j1 aikjxj. Is that okay?
Yeah.
Then now let's take, so this is you have a gradient, and this is the kth component. All right. Is there a better way to do this? I hate this. But now take the m derivative of the xk derivative, right? Right?
Uh-huh.
Huh?
Yes.
Right. So if I take m of this, it becomes mk, and if I take of this, it becomes km, right?
Yeah.
And Oh, yeah, yes. Are you asking, so I think, yeah, we get 2A. Is that your question?
We get AX plus A transpose X.
Right, but, yes. Yeah, that's right. And then, but yeah, our guys were symmetric. So yeah. Yes. Is that okay now?
Yeah.
Okay, good, thank you.
Professor, I had one other question.
Yeah.
So when we were proving the equivalence for the C2 characterization for convexity, you said that we were doing it by proof of contradiction.
Yeah,
So I'm wondering, so we're suppose that we suppose if the Hessian is not positive semi-definite, does that immediately imply that we assume that the Hessian is negative semi-definite? What if it's neither?
no, it would be, so, let's be clear. We want to prove that the Hessian of f of x is non-negative for all x in Rn, right?
Mhm.
What's the contrapositive?
That in this case, when we say it's bigger than 0, we're saying it's like positive semi-definite.
No,
Right?
yeah, but what's the contrapositive?
That for some x, it is not positive semi-definite.
Right, yeah.
But aren't there cases where we have matrices that are neither positive or negative semi-definite?
I mean, how do you say this? Oh, yeah, right. So we can be more specific. So this is negative for some V.
Okay, I see.
Yeah,
Okay then. Okay.
yeah.
Thank you then.
Yep.